So, hello everyone. Welcome to a talk on PMFault, a voltage fault injection on server platforms through the PMBus. I'm Zitai Chen. I'm a last year PhD student in University of Birmingham. I'm interested in fault injection for my analysis and also automotive security. This work is done with David Oswald. You can contact me through those emails because I'm last year PhD student. Maybe the first one may expire soon. Before we're going to talk about this work, let's talk about a kind of evolution of fault injection on Intel platforms. So the first generation of fault injection, voltage-based fault injection, would be a software-based fault injection. It uses the MSR 150. For example, the Plundervolt uses interface by writing to these registers from the CPU. You can change the voltage of CPU, and if you're undervolting, if you lower the voltage of CPU, the CPU may undervolt, and it can inject fault into some RSA-RT, RSA calculation, and also AES-NI. After this was published, Intel actually published a kind of BIOS and microcode upgrade to disable this interface. And so I was thinking, like, can we do this in hardware? So we have the second generation, is a kind of hardware-based fault injection. This is the work I did like several years ago. Is a hardware-based fault injection. We connected another microcontroller to this SVID bus. This SVID bus is actually an interface on the voltage regulator, which controls the voltage of the CPU. And with this kind of method, we can control this voltage regulator through this interface and change voltage and do the same thing as Plundervolt and undervolting to inject faults. And both of these attacks are done in the kind of desktop motherboard. So you may wonder what would be the next for the fault injection. Can it be done on server platforms with this kind of things patched? So we bought a Supermicro X11 server motherboard, and we tried to do the same thing. So the first step is we look into the voltage regulator. So actually, this motherboard uses MP2955 voltage regulator, but we can't find the datasheet. But there is kind of very similar model, 2965. We can find the datasheet of that because the name is kind of very similar. We think maybe it has the same pins. So the first thing we found is, of course, the SVID bus, the SVID pins, which was used in the volt pager. And there is another set of pins that looks quite interesting. It's this SCL, SDA pins. A first look, it looks like I2C interface. And we look into the datasheet. It's actually called PMBus. So it stands for Power Management Bus. And it actually has some specification. It's a I2C-based protocol. And it also has a kind of semi-standardized command set and protocol. That means the PMBus specification specifies some standard command. And the manufacturer is also allowed to define their own commands. As I said, it's kind of really similar to I2C. This is the package structure of it. So as you can see, there is kind of a device address field, and also command or register address, and also another field for the data. That means you can send command to the specific device in the address, and by writing data to the register or reading data to the register, you can interact with this device. And the command set is kind of easy to figure out because we have the PMBus specification and the datasheet. What's need to be figured out in order to do this attack is actually the address of the voltage regulator. This address can be configured like manually through some resistors that's soldered onto the motherboard, and also maybe by setting by sending some command before this motherboard came out. In order to do this, we did a kind of I2C scanning from the CPU. So we use a tool called sqrc tool, and there's a command for scanning this sqrc bus. This is actually code from executing from the CPU. I think we need to distinguish like what's executing from the CPU and what's executing from other part of the system here, because later on you can see that we also have some exploit on other microcontrollers on the motherboard. So first thing you see that there is 12 devices from the scanning. So first you need to see like which one looks like voltage regulator. How do we check like which one looks like regulator? Of course, the first thing is its response to common PMBus command, and also the value returned makes sense. We use this two heuristic to guess if the device is voltage regulator or not. So basically, we use these two commands. We first read Vout. If it's less than 0.55 volts, it's kind of normal voltage for the CPU when in idle. And also, there is a register for the PMBus address. If it equals to the address that we are sending this command to, it's most likely to be a voltage regulator. So actually, we found that from the scanning, this 20 in hex is a address for the voltage regulator. And the next thing we want to do is to change the voltage. So this is also sent from the CPU. We write some code to use this command, this PMBus command, to change the voltage, and send this sqrc command from the CPU. You may think like this will lower the CPU voltage to a value that it can have a fault. So you may think like this is kind of easy, like we can kind of have an attack now, but it's actually not. The CPU stalls after we send this command. So this is pretty strange because if we lower the voltage too much, the CPU should crash. But if we just lower the voltage a little bit, the CPU shouldn't crash, right? This stall happens even if we lower the voltage just a little bit. So this looks pretty strange to me. So we wonder like, is this actually like something wrong with CPU, crash the CPU, or is this stall actually recoverable? I mean, if the CPU recoverable, we can lower the voltage and then change the voltage back. That's a kind of complete cycle for voltage fault injection. So that's the question. But this kind of failed attempt, but at least we know the address of the voltage regulator now. Then the next thing we want to do is kind of connecting a kind of expensive equipment now, Raspberry Pi. We luckily because the Raspberry Pi also supports lib sqrc, we don't need to change our code. In order to check if this stall is recoverable or not, we use the Raspberry Pi to connect to the serial motherboard and do the same command sending to lower the voltage. We see the voltage change, but the CPU stops. That's as expected. And then we set the register back. And the CPU is actually back up running again. That means this stall is kind of recoverable. We can have a kind of attack chain from here. So we send command, lower the voltage, and change the voltage back, and use the POC, proof concept from the Plundervolt, CRT RSA fault injection, like as a target. We got a success. But you may wonder, like I said, this is attempt 0.1. You may wonder why is 0.1? Because we need to connect an external device to the motherboard. That requires us to open the box. And opening the box is not within the threat model of SGX. As previous conversation during the kind of Walt Pillager research. So we look deeper into the system, like to say, is there something in the motherboard that allows us to do the same thing without opening the box? And there's kind of very interesting chip on the motherboard, and the modern motherboard is kind of a complicated device. It's not only have the CPU now. So in the red circle, there is a kind of BMC chip. It's called board management controller. So this controller is usually used in the server motherboard for monitoring the voltage or the temperature and things like that. And we look deeper into this well controller and its connections, and we found this. So actually, this BMC is connected to this PMBus. And also, it has an Ethernet management interface. And apart from that, there is a shared Ethernet management interface, which connects both the BMC and the CPU. And apart from that, there's also a KCS link from the CPU to the BMC. That means the CPU can also, the code running on the CPU can also communicate with the BMC directly through this KCS interface. That means we have this Ethernet connection. That allows us to do this attack remotely, because we just connect a wire, plug a wire into it, we can access both BMC and CPU. Because it's connected, the BMC is connected to the PMBus, we're trying to say, like, can we run the same code that runs on the Raspberry on the BMC? So the first step is kind of easy thinking. Maybe we can get a shell from the BMC. Actually, the BMC have this SS port opening, but it gives a kind of antenna system management shell. It's not a fully functional shell. Sorry, it's not a fully functional shell. It can only allow you to execute a limited set of commands. In the previously, there is kind of secret backdoor command like shell sh that gives you a full functioning shell after you type into this management shell. But in our system, it's not working. So then we're thinking, can we use the ultimate weapon firmware refreshing to have our code running in this BMC? So we did some investigation on the firmware refreshing interface. The first one is a web interface. It is protected by BMC password, and it's also diversified in the Supermicro servers. I think this is nice because it's not by default to admin. That means everyone can log into this web interface and do everything he wants. And the second interface is not that good. So there is a tool called AL update tool. It can be run from the CPU with that KCS interface. If you're using this tool, it's required you to have root access on the CPU, but there is no password required on the BMC side. So we want to unpack the firmware and have our code running into it, but when we were unpacking the firmware and was to say, can we modify it, we say that the firmware is kind of encrypted. But its encryption is kind of a bit mind-blowing because it only encrypts the file system headers in each partition. So the content of the file system is actually not encrypted. It's just we can't see the file structure of the file system, but the content, which you can read the content from the file. Another thing is worth mentioning that actually the keys for encrypting and decrypting these file system headers is in that IPMI.so. It's a dynamic linking library inside the rootfs. So we can actually extract the key from the firmware and then do the decryption and do the encryption back again. So we use, and also the firmware layout is mostly the same as one described in Ellipsum. They did some very nice work on the BMC hacking. And we write our tool to decrypt, modify, and repack the firmware based on these two open source projects. And we reverse engineered the firmware, and we found that there is a file that provides a shell. And so we replace it with our shell script, just with one line of content bin sh. And then we repack our firmware and reflect it via KCS using AL update. And we are able to successfully SSH to it and get root shell. But one thing worth mentioning here is that this libsvrc that we use to write our attack code running in the CPU and Raspberry Pi is not supported in the BMC. So we actually have to implement this library by hand by writing to some registers in the BMC and directly interacting with this sgrc interface. And then we can access the PMBus again and send the same command. And then we are able to do some undervolting of it. Finally, we got attack 1. We can fault injection on SGX without physical access. That means we have another software-based fault injection revived. Plundervolt is kind of old software fault injection, and we have Plundervolt revived. We also did some stability testing with CRT RIC fault injection. And we found that sometimes there's no fault when lowering the voltage, and about 77% of the time we got fault, and 26% of the fault is exploitable. This all test is run. We run 253 tests in more than 500 minutes, and on average we can get a useful fault for 9 minutes. So actually, we actually broke one of the servers during the testing. This happens one day at 3 a.m. I was kind of working at night. It's helping to focus, but I was testing my undervolting code, and it's not working. I'm so frustrated, and why my undervolting code is not working? And I tried to test and test again, and I'm a bit dream coding because it's 3 a.m. And I found this register from the datasheet. I see that we are config letters there. And I think if my undervolting code is not working, maybe something wrong with configuration. And I actually read this register and found that this register is not zeroed out. So I think maybe I can reset to 0 and try again. Maybe I reset the config to the default value. It can work again for my undervolting code. But not. We have a boom. Like the fan of the server is spinning like crazy, and the system actually crashes. And this is what I see from the oscilloscope. Actually, by setting this to 0, we overvolt the CPU. We have the voltage jump to 2.84 watts for 1 millisecond. We have a kind of full video with this link, but I don't think I have time to play it here. I can explain that why is this happening. So when looking into the datasheet, looking deeper into the datasheet about this register, we actually found that there is a bit controlling the VID step. It will allow you to switch between 10 milliwatt per VID step and 5 milliwatt per VID step. So with 10 milliwatt per VID step, the voltage of the CPU can be up to 3 watt. And from the CPU specification, the maximum tolerant voltage for the CPU is normally 1.52 watt. That means we definitely permanently damage the CPU with this overvolting. But as I said, I'm using BMC, like it's a server platform. Maybe there are some tools that we can directly interact with BMC. We found that there is an IPMI tool. There is a subcommand called IPMI tool I2C. It allows us to directly interact with the I2C bus on the BMC, which is also the PMBus. So this can be done via that KCS interface that interfaces from the CPU to the BMC, and also through Ethernet. But if you are using this tool through a KCS interface, you do not need to log into the BMC. And if you are using this tool via Ethernet, it requires you to log in, but the password that you use for login can be cleared with this IPMI tool via KCS. So that means we actually don't need to refresh the firmware anymore. Instead, we can just use this IPMI tool. We first can use this command to create a new user or clear the password of this user, and then set the access level. And then after we're creating this user, we can use the tool through that Ethernet interface and using IPMI I2C command to send the PMBus command to the undervolting. So what do you think? I also using this attack because I also used to do vault pillager. I think this attack is actually nicer than vault pillager. In vault pillager, we have this kind of mass setup with all the wires connected, and sometimes we want to control the temperature to put the device in the fridge. And with this attack, we only need the Ethernet cable connect to the server, and then that's it. We don't need to open the box anymore. It's less messy. So we tested our work on Supermicro X11 motherboard. And the first one is the motherboard we bought. We found this vulnerable. We did both undervolting and overvolting attack on it. And we actually destroyed 2 CPUs. And with this, we also tested on 2 additional X11 motherboards. This 2 motherboard was kindly provided by a friend with remote access, and we can confirm that the voltage regulator model is reachable with a default configuration, and we actually did undervolting to crash the server. And because the overvolting will permanently damage the CPU, so we don't want to cost my friend a fortune. So we didn't do the overvolting on this 2 motherboards. After we responsibly discovered this attack to Supermicro, they published a security advisory on the attack. And they also kindly provided us with a X12 series of motherboard. And we checked that it's not vulnerable. So here's some takeaways for Black Hat soundbites. I think the first one is we need to think a server as an embedded system. So as you can see, there's not only CPU on the motherboard, there are also many other microcontrollers on the motherboard. For example, there is a kind of SAS controller. The most important thing is that BMC for this attack. And sometimes there is also a CPLD on the motherboard. So vulnerability and functionality in one component can affect the rest of the system. If you think this attack, like we're using IPMI tool, right? The IPMI tool, S2C subcommand is kind of a built-in functionality for, it has its intended functionality. It doesn't have the vulnerability by itself. But if you think it in the concept of combining the threat model of SGX, the platform security, you can actually undervolt the CPU, overvolt the CPU through this interface. That's the first takeaway, I think. Apart from that, the system is more of a software and a combination of software and hardware. So when you're thinking of the security of the platform, I think you should think it in 2 directions. With this attack, if there's no connection from the voltage regulator to the BMC, this attack can't happen, right? Because that is because like there's no such interface. That interface is cut out. So one of the reasons that this attack can happen is first thing about the motherboard layout, the wire layout, the connections, and the second thing, the firmware, because of the firmware and the IPMI tool. Apart from that, probably I haven't mentioned this before. So the BMC has its own firmware flash chip. That's an individual flash chip directly connected to the BMC. It's not connected to anywhere else. It's a separate chip than the BIOS flash chip. So we're thinking of SGX security. So SGX cannot reach this BMC firmware because there's no connection from the CPU or the chipset to this flash chip. Apart from that, improper like jumper configuration and wiring can cause a security issue, as I mentioned before. And there are so many more interfaces that is interesting to look at. For example, LPC, SMBus, SPI, S2C, PCIe. So when designing a system, we should carefully look into those wiring, like how those wires should be connected. Should that be actually sharing between components or not? Apart from that, we also have this PMBus detect tool. This tool can allow you to scan the I2C bus with that heuristic to check if there is a device on the I2C bus that looks like a voltage regulator. Because the PMBus specification is kind of semi-standardized specification, there may be some different command set in different voltage regulators. We currently only tested this tool with this tool voltage regulator module. And your contributions are very welcome. Finally, some acknowledgement. Thanks for the EPRC for funding this research, and also thanks Supermicro for providing their X12 serial motherboard for further investigation of this issue. That's all for the talk. So you can scan the QR code there to check our website or GitHub repo. So that's all. I'm open to questions. Any questions? Yeah. Yeah.
In some slide before with the Supermicro servers, there were a few vulnerable and another one that it wasn't vulnerable.
Oh, this one?
Yes.
Yeah.
Do you know exactly why this was not vulnerable?
We have a brief look onto this system, and we think that it implements some I2C command filtering on this platform. So the command that we send to the voltage regulator is kind of blocked for undervolting.
Okay.
Yeah.
Okay, thanks.
Anything else? Yeah. You're also welcome to talk with me afterwards. Yeah, I think that's it. Thank you.